Hello everyone. Today I represent my group to present about the topic language and project Parser. My group have two members, Lưu Quang Vũ and I, Nguyễn Thị Thu Huyền. My presentation is divided into two main parts. The first part is a review of the topic language. The second part is an explanation of the project based on the code file that our group has made. So let's start with the first part, language. The goal is going to be to get computers to understand the way you and I communicate naturally via our own natural languages like English. But natural language contains a lot of nuance and complexity that's going to make it challenging for computers to be able to understand. So we will need to explore some new tools and some new techniques to allow computers to make sense of natural language. So, what is it exactly that we are trying to get computers to do? Well, they all fall under this general heading of natural language processing. We span all tasks where the AI gets human language as input, and these tasks include tasks like automatic summarization, where the AI is given text as input and it produces a summary of the text as output. Information extraction, where the AI is given a corpus of text and the AI extracts data as output. Language identification, where the AI is given text and returns the language of the text as output. Machine translation, like Google Translate, where the AI is given a text in the origin language and it outputs the translation in the target language. Question answering. If you have ever asked a question to your phone or had a conversation with an AI chatbot where you provide some text to the computer is able to understand that text and then generate some text in response. Text classification, where the AI is given text and it needs to classify it as some type of text, positive or negative, inbox or spam, for example. And there are several other kinds of tasks that all fall under this heading of natural language processing. But before we take a look at how the computer may try to solve this kind of task, it might be useful for us to think about language in general. What are the kind of challenges that we might need to deal with as we start to think about language and getting a computer to be able to understand it? So, one part of language that we need to consider is the syntax of language. Syntax is all about the structure of language. Language is composed of individual words, uh, and those words are composed together in some kind of structure whole. And if our computer is going to be able to understand language, it's going to need to understand something about that structure. So let's take a couple of examples. Here, for instance, is a sentence: just before 9 o'clock, Sherlock Holmes stepped briskly into the room. That sentence is made up of words, and those words together form a structure whole. This is syntactically valid as a sentence, but we could take some of those same words, rearrange them, and then come up with a sentence that is not syntactically valid. Here, for example, just before Sherlock Holmes 9 o'clock stepped briskly the room is still composed of valid words, but they are not in any kind of logical whole. This is not a syntactically well-formed sentence. Another interesting challenge is that some sentence will have multiple possible valid structure. Here, a sentence, for example, I saw the man on the mountain with a telescope. This is a valid sentence, but it actually has two different possible structures that lend themselves to two different interpretations and two different meanings. Maybe I, the one doing the seeing, and the one with the telescope, or maybe the man on the mountain is the one with the telescope. And so natural language is ambiguous. Sometimes the same sentence can be interpreted in multiple ways, and that's something that we need to think about as well. And this lends itself to another problem within language that we will need to think about, which is semantic. While syntax is all about structure of natural language, semantic is about the meaning of language. It's not enough for a computer just to know that a sentence is well structured if it doesn't know what that sentence means. So semantic is going to concern itself with the meaning of words and the meaning of sentence. So if we go back to the same sentence as before, just before 9 o'clock, Sherlock Holmes stepped briskly into the room. I will come up with another sentence. A few minutes before 9, Sherlock Holmes walked quickly into the room. And though two different sentences with some of words are the same and some of words different, but the two sentences had essentially the same meaning. And so ideally, whatever the model we build, we will be able to understand that these two sentences, while different, mean something very similar. Some syntactically well-formed sentences don't mean anything at all. A famous example of form language is the sentence "colorless green ideas step furiously." This is a syntactically, structurally well-formed sentence. We have got adjective modifying a noun, ideas. We've got a verb and an adverb in the correct position, but when taken as whole, the sentence doesn't really mean anything. And so, if our computers are going to be able to work with natural language and perform tasks in natural language processing, there are some concerns we will need to think about. We will need to be thinking about syntax, and we will need to be thinking about semantics. So, how could we going about trying to teach computer how to understand the structure of natural language? Well, one approach we may take is by starting by thinking about the rule of natural language. Our natural language have rule. In English, for example, nouns tend to come before verbs. Noun can be modified by adjective, for example. And so if only we could formalize those rules, then we could give those rules to a computer, and the computer could be able to make sense of them and understand them. And so let's try to do exactly what that. We are going to try to define a formal grammar, where formal grammar is some system of rules for generating sentences in a language. This is going to be a rule-based approach to natural language processing. We are going to give the computer some rules that we know about language and have the computer use those rules to make sense of structure of language. And there are a number of different types of formats of formal grammars. Each one of them has slightly different use case. But today, we are going to focus specifically on one kind of grammar known as a context-free grammar. So, how does context-free grammar work? Well, here is a sentence that we might want a computer to generate. She saw the city, and we're going to call each of these words a terminal symbol because one our computer has generated the word. There's nothing else for it to generate. Once it's generated the sentence, the computer is done. We're going to associate each of these terminal symbol with a non-terminal symbol that generated it. So here we got N, which stands for noun, like she or city. We've got V as a non-terminal symbol which stands for verb. And then we have D, which stands for determiner. A determiner is word like the or or an in English, for example. So each of these non-terminal symbol can generate the terminal symbol that we ultimately care about generating. But how do we know, or how does the computer know which non-terminal symbol are associated with which terminal symbol? Well, to do that, we need some kind of rule. Here are some what we call rewriting rule that have a non-terminal symbol on the left-hand side of an arrow, and on the right side is what that non-terminal symbol can be replaced with. So here we are saying the non-terminal symbol N again, which stands for now, could be replaced by any of these options separated by the vertical bars, and could be replaced by she or city or car or Harry. D for determiner could be replaced by the, or an, and so forth. Each of these non-terminal symbols could be replaced by any of these words. We can also have non-terminal symbols that are replaced by other non-terminal symbols. Here, an interesting rule: NP around N bar D N. So what does that mean? Well, NP stands for a noun phrase. Sometimes when we have a noun phrase in a sentence, it's not just a single word, it could be multiple words. And so here we are saying a noun phrase could be just a noun, or it could be a determiner followed by a noun. So we might have noun phrase that's just a noun, like she, that's a noun phrase. Or we could have a noun phrase that a multiple words, something like the city, also act as a noun phrase, but in this case it's composed of two words, a determiner, the, and a noun, city. We could do the same for verb phrase. A verb phrase or VP might be just a verb, or it might be a verb followed by a noun phrase. So we could have a verb phrase that is just a single word like the word walk. Or we could have a verb phrase that is an entire phrase, something like saw the city as an entire verb phrase. A sentence, meanwhile, we might then define as a noun phrase followed by a verb phrase. And so this would allow us to generate a sentence like she saw the city, an entire sentence made up of a noun phrase, which is the word she, and then a verb phrase, which is saw the city, saw, which is a verb, and then the city, which itself is also a noun phrase. And so if we could give this rule to a computer, explaining to it what non-terminal symbol could be replaced by what other symbol, then a computer could take a sentence and begin to understand the structure of that sentence. And so let's take a look at example of how we might do that. And to do that, we are going to use a Python library called NLTK, or Natural Language Toolkit. It contains a lot of helpful features and functions that we can use for trying to deal with and process naturally language. So here we will take a look how we can use NLTK in order to pass a context-free grammar. What you will see in this file first is import NLTK, the Natural Language Toolkit. And the first thing I do is define a context-free grammar, saying that a sentence is a noun phrase followed by a verb phrase. I'm defining what a noun phrase is, defining what a verb phrase is, and then giving some example of what I can do with this non-terminal symbol, D for determiner, N for noun, and V for verb. We are going to use NLTK to pass that grammar. Then we will ask the user for some input in the form of a sentence and split it into words. And then we will use the context-free grammar parser to try to parse that sentence and print out the resulting syntax tree. So let's take a look at an example. I ask to type in a sentence, she walked, and when I do that, I see the she walked is a valid sentence where she is a noun phrase and walk is a corresponding verb phrase. I could try to do this with a more complex sentence. She saw the city, and here we see that she is a noun phrase, and then saw the city is an entire verb phrase that make up this sentence. So this allows us to get a sense for the structure of natural language, but it relies on us writing all of these rules, and it would take a lot of effort to write all of the, the rules for any possible sentence that someone may write or say in English language. Language is complicated, and as a result, there are going to be some very complex rules. So what else may we try? We might try to take a statistical lens toward approaching this problem of natural language processing. If we were able to give the computer a lot of existing data of sentences written in the English language, what could we try to learn from that data? Well, it might be difficult to try and interpret long pieces of text all at once. So instead, what we might want to do is break up that longer text into smaller pieces of information instead. In particular, we may try to create n-gram out of a longer sequence of text. An n-gram is just some contiguous sequence of n items from a sample of text. It might be n character in a row or n word in a row, for example. So let's take a passage from Sherlock Holmes and let's look for all of the trigram. A trigram is an n-gram where n is equal to 3. So in this case, we are looking for a sequence of 3 words in a row. So the trigram here would be phrase like, how often that 3 words in a row. Often have I is another trigram. Have I said to you that. They are all trigram sequence of 3 words that appear in sequence. And if we could give the computer a large corpus of text and have it pull out all of the trigram in this case, it could get a sense for what sequence of 3 words tend to appear next to each other in our own natural language, and as a result, get some sense for what the structure of language actually is. And we were able to do this Essentially, while a process known as tokenization, tokenization is the process of splitting a sequence of characters into pieces. In this case, we are splitting a long sequence of text into individual words and then looking at sequences of those words to get a sense for structure of natural language. So once we have done the tokenization, once we build up our corpus of n-gram, what we can do with that information? Well, the one thing that we may try is we could build a Markov chain, which you may recall from when we talked about probability. Recall that a Markov chain is some sequence of values where we can predict one value based on the values that came from before it. And as a result, if we know all of the common n-gram in the English language, what would tend to be associated with what other word in sequence, we can use that to predict what word might come next in a sequence of words. And so we could build a Markov chain for language in order to try to generate natural language that follow the same statistical pattern as some input data. For example, using trigram after the Markov model has two words, it can choose a third one from probability distribution based on the first two. Then it can choose a fourth word from a probability distribution based on the second and third word. So let's now turn our attention to a slightly different problem, and that's the problem of text classification. Text classification is a problem where we have some text and we want to put that text into some kind of category. We want to apply some sort of label to that text, and this kind of problem show up in a wide variety of places. A common place might be your email inbox. For example, you get an email and you want your computer to be able to identify whether the email belongs in your inbox or whether it should be filtered out into spam. So we need to classify the text. Is it a good email or is it spam? Another common use case is sentiment analysis. We may want to know whether the sentiment of some text is positive or negative, and so how might we do that? This comes up in situations like product review, where we might have a bunch of review for product on some website. My grandson loved it, so much fun. Product broke after a few days. One of the best game I played in a long time, and kind of cheap and flimsy. Not worth it. Here's some example sentences that you might see on a product review website, and you and I could pretty easily look at the list of product review and decide which one are positive and which one are negative. We may say the first one and the third one, those seem like positive sentiment message, but the second one and the fourth one seem like negative sentiment message. But how did we know that? And how could we train a computer to be able to figure that out as well? Well, you may have clue your eye in our particular keyword, where those particular words tend to mean something positive or negative. So you may have identified words like love and fun and best tend to be associated with positive messages, and words like broke and cheap and flimsy tend to be associated with the negative messages. So, if only we could train a computer to be able to learn what words tend to be associated with positive versus negative message, then maybe we could train a computer to do this kind of sentiment analysis as well. So we are going to try to do just that. We are going to use a model known as a back-upward model, which is a model that represents text as just an unordered collection of words. For the purpose of this model, we are not going to worry about the sequence and the ordering of the word, which word came first, second, or third. We are just going to treat the text as a collection of words in no particular order, and we are losing information there, right? The order of words is important, and we will come back to that a little bit later. But for now, to simplify our model, it will help us tremendously just to think about text as some unordered collection of words, and in particular, we are going to use the back-upward model to build something known as a naive-based classifier. So what is a naive-based classifier? Well, it's a tool that's going to allow us to classify text based on Bayes' rule. Again, which you might remember from we talk about probability. Bayes' rule say that the probability of B given A is equal to probability of A given B multiplied by the probability of B divided by the probability of A. So, how are we going to use this rule to be able to analyze text? What are we interested in? We are interested in the probability that a message has positive sentiment and the probability that a message has negative sentiment, which I'm here for simplicity going to present just with this emoji, happy face and frown face as positive and negative sentiment. And so if I had a review, something like my grandson love it, then what I'm interested in is not just the probability that a message has positive sentiment, but the conditional probability that a message has positive sentiment, given that this is a message. My grandson love it. But how do I go about calculating this value? The probability that the message is positive given that the review is this sequence of words. Well, here's where the back-upward model comes in. Rather than treat this review as a string of a sequence of words in order, we're just going to treat it as an unordered collection of words. We're going to try to calculate the probability that the review is positive, given that all of these words my grandson love it are in the review in no particular order, just this unordered collection of words. And this is a conditional probability which we can then apply Bayes' rule to try to make sense of. So according to Bayes' rule, this conditional probability is equal to the probability that all of these forward are in the review. Given that the review is positive, multiply by the probability that the review is positive divided by the probability that all of these words happen to be in the review. So this is the value now that we are going to try to calculate. Now, one thing you might notice is that the denominator here, the probability that all of these words appear in the review doesn't actually depend on whether or not we are looking at the positive sentiment or negative sentiments case. So we can actually get rid of this denominator. We don't need to calculate it. We can just say that this probability is proportional to the numerator, and then at the end we're going to need to normalize the probability distribution to make sure that all of the value sum up to the value 1. So now, how do we calculate it? This value, well, this is a probability of all of these words given positive time, probability of positive, and that by the definition of joint probability is just one big joint probability. The probability that all of these things are the case. That is a positive review, and that all four of these words are in the review. But still, it's not entirely obvious how we calculate that value, and here is where we need to make one more assumption, and this is where the ninth part of 9b comes in. We're going to make the assumption that all of the words are independent of each other. And by that, I mean that if the word grandson is in the review, that does change the probability that the word love is in the review or that the word it is in the review, for example. And in practice, this assumption may not be true. It almost certainly the case that the probability of work do depends on each other, but it's going to simplify our analysis and still give us reasonably good result just to assume that the words are independent of each other and they only depend on whether it's positive or negative. You may, for example, expect the word love to appear more often in a positive review than in a negative review. So what does it mean? Well, if we make this assumption, then we can say that this value, the probability we interest in is not directly proportional to, but is naively proportional to this value. The probability that the review is positive time, the probability that my is in the review given that is positive time, the probability that grandson is in the review given that is positive, and so on for the other two words that happen to be in this review. And now this value, which look a little more complex, is actual value that we can calculate pretty easily. So how are we going to estimate the probability that the review is positive? Well, if we have something training data, some example data of example review where each one has already been labeled as positive or negative, then we can estimate the probability that a review is positive just by counting the number of positive samples and dividing by the total number of samples that we have in our training data. And for the conditional probability, the probability of love given that it's positive, well, that's going to be the number of positive sample with love in it divided by the total number of positive sample. So let's take a look at an actual example to see how we could try to calculate this value. Here, I'll put together some sample value. The way to interpret the sample data is that based on the training data, 49% of the review are positive, 51 are negative. And then over here, in this table, we have some conditional probability. We have if the review is positive, then there's a 30 30% chance that might appear in it. And if the review is negative, there's a 20% chance that might appear in it. And based on our training data, among the positive review, 1% of them contain the word grandson, and among the negative review, 2% contain the word grandson. So using this data, let's try to calculate this value, the value we interested in. And to do that, we will need to multiply all of this value together, the probability of positive, and then all of these positive conditional probabilities. And when we do that, we get some value. And then we can do the same thing for the negative case. Take the probability that is negative, multiply it by all of this conditional probability, and we're going to get some other value. And now this value don't sum to 1. They are not a probability distribution yet, but I can normalize them and get some value, and that tell me that we are going to predict that my grandson love it. We think there are a 68% chance probability is 0.68. That is a positive sentiment review, and 0.32 probability that is a negative review. So what problem might we run into here? We could potentially go wrong when doing this kind of analysis. In order to analyze whether the text has a positive or negative sentiment, well, a couple of problems might arise. One problem might be, what if the word grandson never appear for any positive review? If that were the case, then when we try to calculate the value, the probability that we think the review is positive, we're going to multiply all this value together, and we are just going to get O for the positive case, because we are going to ultimately multiply by that O value. So we are going to say that we think there is no chance that the review is positive because it contains the word grandson, and in our training data, we have never seen the word grandson appear in a positive sentiment message before, and that probability not the right analysis, because in case of rare word, it may be the case that in now where in our training data, did we ever see the word grandson appear in a message that has positive sentiment? So, what can we do to solve this problem? Well, one thing we often do is some kind of additive smoothing, where we add some value alpha to each value in our distribution just to smooth out the data a little bit. And a common form of this is Laplace smoothing, where we add on 1 to each value in our distribution. In essence, we pretend we have seen each value one more time than we actually have. If we have never seen the word grandson for a positive review, we pretend we have seen it once. If we have seen it once, we pretend we have seen it twice, just to avoid the possibility that we might multiply by zero, and as a result, get some result we don't want in our analysis. And so, this definitely is a useful tool that we can use to try and make some prediction. Well, we have seen a couple of times now that when we want to take some data and take some input, put it in a way that the computer is going to be able to make sense of, it can be helpful to take that data and turn it into number ultimately. And so what we may want to try to do is come up with some word representation, some way to take a word and translate meaning into number. Because, for example, if we want to use a neural network to be able to process language, give our language to a neural network and have it make some prediction or perform some analysis there. A neural network takes as input and produce as output a vector of value, a vector of numbers. And so what we might want to do is take our data and somehow take words and convert them into some kind of numeric representation. So how might we do that? How might we take words and turn them into number? Let's take a look at an example. Here's a sentence. He wrote a book, and let's say I wanted to take each of those words and turn it into a vector of value. Here's one way I may do that. We will say he is going to be a vector that has a 1 in the first position and the rest of the value are 0. Row will have a 1 in the second position and the rest of the value are all. A hash a 1 in the third position with the rest of the value 0, and book has a 1 in the fourth position with the rest of the value 0. So each of these words now has a distinct vector representation. And this is what we often call a one-hot representation, a representation of the meaning of a word as a vector with a single one and all of the rest of the value are 0. And so when doing this, we now have a numeric representation for every word. And we could pass in those vector representation into a neural network or other model that requires some kind of numeric data as input. But this one-hot representation actually has a couple of problems and is not ideal for a few reasons. One reason is here we're just looking at forward, but if you imagine a vocabulary of thousands of words or more, these vectors are going to get quite long in order to have a distinct vector for every possible word in our vocabulary. And as a result of that, these longer vectors are going to be more difficult to deal with, more difficult to train, and so forth. And so that might be a problem. Another problem is a little bit more subtle. If we want to represent a word as a vector, and in particular, the meaning of a word as a vector, then ideally it should be the case that the word that have similar meaning should also have similar vector representation so that we are close to each other together inside a vector space. But that's not really going to be the case with this one-hot representation, because if we take some similar word, say the word wrote and the word author, which means similar thing, they have entirely different vector representation. Likewise, book and novel, those two words mean somewhat similar thing, but they have entirely different vector representation because they each have a one in some different position, and so that not ideal either. So what we might be interested in instead is some kind of distributed representation. A distributed representation is a representation of the meaning of a word distributed across multiple values instead of just being one hot with a one in one position. Here is what a distributed representation of word might be. Each word is associated with some vector of value with the meaning distributed across multiple values, ideally in such a way that similar words have a similar vector representation. But how are we going to come up with those values? Where do those values come from? How can we define the meaning of a word in this distributed sequence of numbers? Well, to do that, we are going to draw inspiration from a quote from British linguist who said, "You shall know a word by the company it keeps." In other words, we are going to define the meaning of a word based on the word that appear around it, the context words around it. Take for example this context for blind. You may wonder what word could reasonably fill in that blank. Well, it may be a word like breakfast or lunch or dinner. All of those could reasonably fill in that. And so what we are going to say is because does the word breakfast and lunch and dinner appear in a similar context, that they must have a similar meaning, and that something our computer could understand and try to learn. A computer could look at a big corpus of text, look at what would tend to appear in similar context to each other, and use that to identify which words have a similar meaning and should therefore appear close to each other inside a vector space. And so one common model for doing this is known as a word-to-word model. It's a model for generating word vector, a vector representation for every word by looking at data and looking at the context in which a word appears. The idea is going to be this. If you start out with all of the words just in some random position in space and train it on some training data, what the work to model will do is start to learn what words appear in similar contexts, and it will move this vector around in such a way that hopefully what with a similar meaning breakfast, lunch and dinner, book, memoir, novel will hopefully appear to be near to each other as vector as well. One other interesting side effect of word-to-word is that it also able to capture something about the relationship between words as well. Let's take a look at example, here for instance are two words, man and king, and these are each represented by word to word as a vector. So what might happen if I subtracted one from the other, calculated the value king minus man? Well, that will be the vector that will take us from man to king, somehow represents this relationship between the vector representation of the word man and the vector representation of the word king. And that's what this value king minus man represent. So what would happen if I took the vector representation of the word woman and added that same value king minus man to it? What would we get as the closest word to that? For example, well, we could try it. I could say, what is the closest word to the vector representation of the word king minus the representation of the word man plus the representation of the word woman, and the closest word is the word queen. We have somehow been able to capture the relationship between king and man, and then we apply it to the word woman. We get as a result the word queen. So, word to word has been able to capture not just the word and how they are similar to each other, but also something about the relationship between words and how those words are connected to each other. So now that we have this vector representation of word, what can we now do with it? Now we can represent word as number, and so we might try to pass those words as input to say a neural network. Neural network, we have seen a very powerful tool for identifying pattern and making prediction. We call that a neural network. You can think of as all of this unit, but really what the neural network is doing is taking some input, passing it into network, and then producing some output. And by providing the neural network with training data, we're able to update the way inside of the network so that the neural network can do a more accurate job of translating those input into those output. And now that we can represent what as number that we could be the input or output, you could imagine passing a word in as input to a neural network and getting a word as output. And so when might that be useful? One common use for neural network is in machine translation when we want to translate text from one language into another, say translate English into French by passing English into neural network and getting some French output. You may imagine, for instance, that we could take the English word for lamb, pass it into the neural network, and get the French word for lamb as output. But in practice, we have translating text from one language to another. We usually not just interested in translating a single word from one language to another, but a sequence, say a sequence or paragraph of words. Here, for example, is another paragraph, again taken from Sherlock Holmes written in English. And What I might want to do is take that entire sentence, part it into neural network, and get as output a French translation of the same sentence. But recall that a neural network input and output need to be of some fixed size, and a sentence is not a fixed size, it's a variable. You may have shorter sentences and you might have longer sentences. So somehow we need to solve the problem of translating a sequence into another sequence by means of a neural network. And that's going to be true not only for machine translation but also for other problems. The problem like question answering. If I want to pass as input a question, something like what is the capital of Massachusetts? Feed that as input into neural network. I would hope that what I would get as in output is a sentence like the capital is Boston. Again, translating some sequence into some other sequence. And if you ever had a conversation with an AI chatbot or have ever asked your phone a question, you need to do something like this. You need to understand the sequence of words that you, the human, provide as input, and then the computer needs to generate some sequence of words as output. So, how can we do this? Well, one tool that we can use is a recurrent neural network, which a way for us to provide a sequence of value to a neural network by running the neural network multiple times. And each time we run the neural network, we're going to keep track of some hidden state, and that hidden state is going to be passed from one run of the neural network to the next run of the neural network. Keep track of all of the relevant information. And so let's take a look at how we could apply that to something like this. And in particular, we're going to look at an architecture now as an encoder decoder architecture, where we are going to encode this question into some kind of hidden state, and then use a decoder to decode that hidden state into the output that we are interested in. So what's that going to look like? We will start with the first word, the word what. That's going into our neural network, and it's going to produce some hidden state. This is some information about the word what that our neural network is going to need to keep track of. Then when the second word come along, we're going to feed it into that same encoder neural network, but it's going to get as input that hidden state as well. So we pass in the second word. We also get the information about the hidden state, and that's going to continue for the other word in the input. This is going to produce a new hidden state, and so then when we get to the third word, the that's go into the encoder, it also get access to the hidden state, and then it produce a new hidden state that gets passed into the next run when we use the word capital. And the same thing is going to repeat for the other word that appear in the input. So of Massachusetts, that produce one final piece of hidden state. Now somehow we need to signal the fact that we we have done. There's nothing left in the input, and we typically do this by passing some kind of special token, say N token, into neural network. And now the decoding process is going to start, going to generate the word the, but addition to generating the word the, this decoder network is also going to generate some kind of hidden state. And so what happened the next time? Well, to generate the next word, it might be helpful to know what the first word was. So we might pass the first word, the, back into the decoder network. It's going to get as input the hidden state and it's going to generate the network capital. Um, and that's also going to generate some hidden state, and we will repeat that, passing capital into the network to generate the third word is, and then one more time in order to get the fourth word Boston. And at that point we have done, but how do we know what we have done? Usually we will do this one more time, pass Boston into decoder network and get as output some n token to indicate that that is the end of our input. And so this then is how we could use a recurrent neural network to take some input, encode it into some hidden state, and then use that hidden state to decode it into the output we ingest in. To visualize it in a slightly different way, we have some input sequence. This is just some sequence of words. That input sequence goes into the encoder, which in this case is a recurrent neural network generating this hidden state along the way until we generate some final hidden state, at which point we start the decoding process. Again, using a recurrent neural network that's going to generate the output sequence as well. So we have got the encoder, which is encoding the information about the input sequence into this hidden state, and then the decoder, which takes that hidden state and use it in order to generate the output sequence. But there are some problem, and for many years this was the state of the at the recurrent neural network, and variant on this approach was some of the best way we know in order to perform tasks in natural language processing. But there are some problems that we might want to try to deal with, and that we have been deal with over the year to try and improve the point this kind of model. And one problem you may notice happen in this encoder state, we have taken this input sequence, the sequence of word, and encoded it all into this final P of hidden state, and that final P of hidden state need to contain all of the information from the input sequence that we need in order to generate the output sequence. And why that's possible? It becomes increasingly difficult as the sequence gets larger and larger. For large and larger input sequence, it's going to become more and more difficult to store all of the information we need about the input inside this single hidden state piece of context. That's a lot of information to pack into just a single value. It might be useful for us when generating output to not just refer to this one value, but to all of the previous hidden value that have been generated by the encoder, and so that might be useful. But how could we do that? We have got a lot of different value, we need to combine them somehow. So you could imagine adding them together, taking the average of them, for example. But doing that would assume that all of these P of hidden state are equally important. But that's not necessarily true either. Some of these P of hidden state are going to be more important than other, depending on what word they most closely correspond to. This P of hidden state very closely correspond um, to the first word of the input sequence. This one very closer correspond to the second word of the input sequence, for example, and some of those are going to be more important than other. To make matter more complicated depending on which word of the output sequence we are generating, different input words may be more or less important. And so what we really want in some way to decide for ourselves which of the input value are worth paying attention to at what point in time. And this is the key idea behind a mechanism known as attention. Attention is all about letting us decide which value are important to pay attention to when generating in this case the next word in our sequence. So let's take a look at example of that. Here a sentence. What is the capital of Massachusetts? Same sentence as before. And let's imagine that we are trying to answer that question by generating token of output. So what would the output look like? Well, it's going to look like something like the capital is, and let's say we are now trying to generate this last word here. What is the last word? How is the computer going to figure out? Well, what it's going to need to do is decide which value it's going to pay attention to. And so the attention mechanism will allow us to calculate some attention score for each word, some value corresponding to each word, determining how relevant it is for us to pay attention to that word right now. And in this case, when generating the first word of the output sequence, the most important word to pay attention to might be capital and Massachusetts. For example, that's the words are going to be particularly relevant, and there are a number of different mechanisms that have been used in order to calculate this attention score. It could be something as simple as a dot product to see how similar two vectors are, or we could train an entire neural network to calculate this attention score. But the key idea is that during the training process for our neural network, we are going to learn how to calculate this attention score. Our model is going to learn what is important to pay attention to in order to decide what the next word should be. So, the result of all of this calculating this attention score is that we can calculate some value for each input, determining how important is it for us to pay attention to that particular value, and recall that each of these input word is also associated with one of these hidden state context vector, capturing information about the sentence up to that point, but primarily focus on that word in particular. And so what we can now do is if we have all of these factors and we have value representing how important is it for us to pay attention to the particular vector is we can take a weighted average. We can take all of these factors, multiply them by their attention score, and add them up to get some new vector value, which is going to represent the context from the input, but especially paying attention to the words that we think are most important. And once we have done that, that context vector can be fed into our decoder in order to say that the word should be, in this case, Boston. So attention is a very powerful tool that allow any word when we are trying to decode it to decide which word from the input should we pay attention to in order to determine what's important for generating the next word of the output. And so when we combine the attention mechanism with a recurrent neural network, we can get very powerful and useful result where we are able to generate an output sequence by paying attention to the input sequence too. But there are other problem with this approach of using a recurrent neural network as well. In particular, notice that every run of the neural network depends on the output of the previous step, and that was important for getting a sense for sequence of word and the ordering of the particular word. But we can run this unit of neural network until after we have calculated the hidden state from the run before it, from the previous input token. And what that means is that it's very difficult to parallelize this process. That as the input sequence get longer and longer, we might want to use parallelism to try and speed up this process of training the neural network and making sense of all of this language data. But it's difficult to do that, and it's slow to do that with a recurrent neural network because all of this need to be performed in a sequence, and that's become an increasingly challenging challenge as we have started to get larger and larger language model. The more language data that we have available to us to use to train our machine learning model, the more accurate it can be, the better representation of language it can have, the better understanding it can have, and the better result that we can see. And so we have seen this growth of large language models that are using large and large data set, but as a result, they take longer and longer to train. So this problem that recurrent neural networks are not easily to parallel has become an increasing problem, and as a result of that, um, that was one of the main motivation for different architecture for thinking about how to deal with natural language, and that's known as a transformer architecture. And this has been a significant milestone in the world of natural language processing for really increasing how we how well we can perform this kind of natural language processing task, as well as how quickly we can train a machine learning model to be able to produce effective results. There are a number of different types of transformer in terms of how they work, but what we are going to take a look at here It's the basic architecture for how one might work with a transformer to get a sense for what's involved and what we're doing. So let's start with the model we were looking at before, especially at this encoder part of our encoder-decoder architecture, where we use a recurrent neural network to take this input sequence and capture all of this information about the hidden state and the information we need to know about that input sequence. Right now, it all needs to happen in this linear progression. But what the transformer is going to allow us to do is process each of the words independently in a way that easily to parallel rather than have each word way. For some other word, each word is going to go through this same neural network and produce some kind of encoded representation of that particular input word. And all of this is going to happen in parallel. Now, it's happening for all of the words at once, but we are really just going to focus on what happened for one word to make it clear. But now, that's whatever you seeing happen for this one word is going to happen for all of the other input word too. So what's going on here? Well, we start with some input word. That input word goes into neural network, and the input is hopefully some encoded representation of the input word. The information we need to know about the input word that's going to be relevant to us as we generating the output. And because we were doing this each word independently, it's easy to parallelize. We don't have to wait for a previous word before we run this word through the neural network. But what did we do in this process by trying to parallelize this whole thing? Well, we have lost all notion of word ordering. The order of words is important. The sentence Sherlock Holmes gave the book to Watson has a different meaning than Watson gave the book to Sherlock Holmes. And so we want to keep track of that information about word position in the recurrent neural network that happened for us automatically because we could run each word one at a time through the neural network, get the hidden state, add it on to the next run of the neural network. But that's not the case here with the transformer, where each word is being processed independent of all of the other one. So what are we going to do to try to solve that problem? One thing we can do is add some kind of positional encoding to the input word. The positional encoding is some vector that represent the position of the word in the sentence. This is the first word, the second word, the third word, and so forth. We are going to add that to input word, and the result of that is going to be a vector that captures multiple pieces of information. It captures the input word itself as well as where in the sentence it appears. The result of that is we can pass the output of that addition, of the input word and the positional encoding into neural network. That way the neural network know the word and where it appear in the sentence and can use both those piece of information to determine how best to represent the meaning of that word in the encoded representation at the end of it. In addition to what we have here, in addition to positional encoding and this feed-forward neural network, we also going to add one additional component, which is going to be a cell attention step. This is going to be attention where we are paying attention to other input words because the meaning or interpretation of an input word might vary depending on the other word in the input as well. And so we are going to allow each word in the input to decide what are the words in the input it should pay attention to in order to decide on its encoded representation, and thus going to allow us to get a better encoded representation for each word because words are defined by their context, by the word around them, and how they use in that particular context. This kind of self-attention is so valuable in fact that oftentimes the transformer will use multiple different self-attention layers at the same time to allow for this model to be able to pay attention to multiple phases of the input at the same time. We call this multiple header attention, where each attention head can pay attention to something different, and as a result, this network can learn to pay attention to many different parts of the input for the input work all at the same time. And in the spirit of deep learning, these two steps, this multi-headed cell attention layer and this neural network layer, that itself can be repeated multiple times too in order to get a deeper representation, in order to learn deeper pattern within the input text and ultimately get a better representation of language in order to get useful and coded representation of all of the input words. And so this is the process that a transformer might use in order to take an input word and get it as encoded representation. And the key idea is to really rely on this attention step in order to get information that's useful in order to determine how to encode that word. And that process is going to repeat for all of the input words that are in the input sequence. We're going to take all of the input words, encoded them with some kind of positional encoding, feed those into this cell attention and feed forward neural network in order to ultimately get this encoded representation of word. That's the result of the encoder. We get all of the encoded representation that will be useful to us when it comes time then to try to decode all of this information into the output sequence we interest in. And again, this might take place in the context of machine translation, where the output is going to be the same sentence in a different language, or it might be an answer to a question in the case of an AI chatbot, for example. And so now let's take a look at how that decoder is going to work. Ultimately, it's going to have a very similar structure. Anytime we are trying to generate the next output word, we need to know what the previous output word is, as well as its positional encoding, where in the output sequence are we. And we're going to have this same step, self attention, because we might want an output word to be able to pay attention to other word in that same output, as well as neural network. And this might itself repeat multiple times. But in this decoder, we are going to add one additional step. We are going to add an additional attention step, where in cell attention, where the output word is going to pay attention to other output word. In this step, we are going to allow the output word to pay attention to the encoded representation. So we call that the encoder is taking all of the input word and transforming them into this encoded representation of all of the input word. But it's going to be important for us to be able to decide which of the encoded representation we want to pay attention to when generating any particular token in the output sequence. And that's what this additional attention step is going to allow us to do. It's saying that every time we are generating a word of the output, we can pay attention to the other word in output, because we may want to know what are the words we generate previously, and we want to pay attention to some of them to decide what word is going to be to be next in the sequence. But we also care about paying attention to the input word too, and we want the ability to decide which of these encoded representation of the input word are going to be relevant in order for us to generate the next step. And so these two P combined together, um, we have this encoder that take all of the input word and produces encoded representation, and we have this encoded that is able to take the previous output word, pay attention to that encoded input, and then generate the next output word. And this one of the possible architecture we could use for a transformer, with the key idea being this attention step that allow us to pay attention to each other during the training process. Here, we can now much more easily parallelize this, because we don't have to wait for all of the work to happen in sequence, and we can learn how we should perform this attention step. The model is able to learn what's important to pay attention to, what thing do I need to pay attention in order to be more accurate at predicting what the output work is. And this has proved to be a tremendously effective model for conversation AI agent for building machine translation system, and there have many variants proposed on this model too. Some transformer only use an encoder, some only use a decoder, some use some other combination of these different particular feature, but the key idea ultimately remains the same. It's really focused on trying to pay attention to what is most important. That's all about the topic language, and the next we will move to the second part, the project Parser. A common task in natural language processing is parsing. the process of determining the structure of a sentence. This is useful for a number of reasons. Knowing the structure of a sentence can help a computer to better understand the meaning of the sentence, and it can also help the computer extract information out of a sentence. In particular, it's often useful to extract noun phrase out of a sentence to get an understanding for what the sentence is about. In this problem, we will use a context-free grammar formalism to parse English sentences to determine their structure. The first thing you will see in this file is that I import NLTK, which is a powerful library for working with human language data. I also import this for handling command line argument. Next, I define a context-free grammar. This grammar detects the structure of valid sentence by specifying what makes up a sentence, a noun phrase, and a verb phrase. This section lists different parts of speech such as adjective, noun, verb, and more. Now I define the non-terminal symbol, which determine how phrase and sentence are formed. Here I define S as a sentence that consists of a noun phrase followed by a verb phrase. The grammar also defines how adjective phrase, prepositional phrase, and adverb phrase are structured. After defining the grammar, I use NLTK GFG.FromString method to create the grammar and then initialize a parser using char parser. Now let's move on to the main function. It handles input from either a file or the user's keyboard. This part reads a sentence from a file if a file name is provided. Otherwise, it prompts the user to enter a sentence manually. Before passing the sentence, I pre-process it to ensure it is in a suitable format. The function pre-process convert all characters to lowercase and remove any words that do not contain at least one alphabetic character. Once the sentence is processed, we attempt to pass it using parser pass. If the sentence is valid according to our grammar, we print it pass 3. If passing is successful, we use an UTK ready print method to display the pass tree in a readable format. One key feature of this project is noun phrase chunking. A noun phrase chunk is a minimal noun phrase that does not contain another NP inside it. This function extracts them from the pass tree. We then print this extract noun phrase. Finally, we ensure that the script runs when executed directly. Now, let's see how the program processes different example sentences. Here I have 10 file text and I will run each file. So let's open the terminal and type python parser.py with text file 1 home start, and then we have np is home and vp is sad. So let's move to the second file. The second file we have the sentence is home lit a pie. So we will run Python parser.py with 2.txt and we have np is home and vp is lit a pie. So continue with the next file. We arrive the day before Thursday and run it. We have NP is we, VP is arrive the day before Thursday. And next with the fourth sentence, Holmes sat in the red armchair and he got run it and we have NP is home, BP is sat in the red armchair, followed by the conjunction and another VP he got. Move to the next example. My companion smile, an enigmatical smile. We have NP is my companion and VP is my an enigmatical smile. The next example, Holmes shouted to himself. We have NP is home and VP is shouted to himself. The next example, she never said a word until we were at the door here. We have NP is she, VP is never said a word, followed by a conjunction until and another clause. We were at the door here. The next example, Home sat down and lit his pie. We have NP is home, VP sat down, followed by the conjunction and another VP lit his pie. The next example, I had a country walk on Thursday and came home in a terrible mess. We have NP is I, VP is had a country walk on Thursday, followed by conjunction and another VP came home in a terrible mess. And the last example, I had a little moist red pan in the palm of my hand. We have NP is I, VP is had a little moist red pan in the palm of my hand. So this is all about my presentation. Thank you for your listening.